Hello, my name is Riya Patel,
And I'm Anushka Chinoy.
and today we'll be presenting an analysis and optimization of incorporation of caffeine into a quantitative model of fatigue and sleep.
In 2011, a study was conducted to analyze how caffeine affects sleep and may induce fatigue, based off of how it directly interacts with homeostatic drive and cholinergic activity in the human body. To construct models that would directly target these components, a model for caffeine concentration in the body, developed by Garibaldi and Perrier in 1975, was used as a foundation. This model uses four key variables: Z of C for caffeine concentration in the body, Z of A for caffeine concentration at the absorption site, also referred to as the dosage, K of A for the constant absorption rate of caffeine, and K of E for the constant elimination rate of caffeine. Z of C and K of E are proportional to each other, while Z of A and K of A are proportional to each other. The rate of caffeine concentration in the body over time, Z of C over dt, is a function of the difference between absorption concentration and elimination concentration.
With discussing the variables as presented in the previous slide, a few variables to note is gamma, which is the value of discrete dose given in the value milligrams per kilograms, as well as time. This model of caffeine concentration ZC incorporates Ka as well as Ke. The rate of absorption is proportional to the dosage, as the rate of elimination is proportional to the caffeine concentration in the body, as represented in equation 1 as well as equation 2. Ke and Ka values are given as the following. Ka equals 1 times 10 to the negative 3 inverse seconds, as Ke is given as 4.5 times 10 to the negative 5th inverse seconds. With these values in mind, an analytical solution was provided as seen in equation 3, in which the caffeine concentration should dramatically increase before exponentially decreasing over time. With these parameters in mind, it is important to consider the role of the discrete dose value gamma. To see this effect of the parameter, the initial condition for the dose was ZA, which is 130 milligrams per 75 kilograms. As for the second simulation was given as ZA equals 260 milligrams per 75 kilograms, which was double from the first simulation. The results are the following as represented in the block diagram. The block diagram represents the equations 1 and 2, which will then reflect the results.
For the first simulation, the model was run for a total of 24 hours, or 8.64 times 10 to the 4th seconds. The first graph on the top right shows the overall model over the entire time period, in which you can see it dramatically increasing and then exponentially decreasing over time as predicted by the analytical solution. The x-axis is represented by time in seconds, and the y-axis is the concentration of caffeine in the body in milligrams per kilograms, or Z of C. On the bottom right graph, you can see a zoomed in version of the peak of the graph, showing that the concentration in the body, Z of C, peaked at about 1.49 milligrams per kilograms at about 2,840 seconds. For the second simulation, the same amount of time was run with the same axes, but this time the initial condition for the dosage, Z of A, was given as 260, double the previous one. This showed that the concentration in the body this time peaked at about 2.99 milligrams per kilograms at about 3,450 seconds, but the graph still remains the same shape as nothing else was changed. This is the referenced article, Incorporation of Caffeine into a Quantitative Model of Fatigue and Sleep, shown, where further information about such effects of caffeine can be found.